Yes.
Wondering. But
Where are they? I don't know.
sure it's not.
They seem to be not here together. Okay.
Well, they are. Together, I guess, right?
It's not called that. Well, it would be under spinning rides.
Are we ready to go?
No.
It's
I have
taping.
not found a name of this thing yet.
I just figured I'd get some pre-class
Also, you are taping.
chitter chatter.
Okay. All right, we're taping. Nice. All righty. Yeah. Oh my God. I know. Jeez, you are dissing me.
I just want our friends to learn me.
That is a good thing, actually. I support that. I mean, I support that thing.
Yeah.
No, but that was your sensitive side.
Yeah.
That was my sensitive side. I don't want anybody in this class.
Okay, I can't really hear you. Goodbye. Okay, I can't really hear you.
Alrighty then. So, separation of variables, because variables, like people, are in fact better off without friends, as we've established. So, how many of you have done separation of variables before? You have? This is Dr. Harmon? Wow, okay.
No way.
Have you been? I didn't think I see you. Yeah, you have. Okay, so you guys have done this sort of thing before. Certainly you've done it if you've done quantum. You may have done it in differential equations, whatever. But you know, it never hurts to pound things into our heads. See it 13 times, and then it finally catches on. And we'll do it first in Cartesian coordinates, then we'll do it in spherical coordinates. So the idea is that we're going to look for solutions for the potential that are of the form of being a product of a function of x only, a function of y only, and indeed a function of z only. Of course, those are not the most general solution, but on the other hand, you can write general solutions in terms of sums over, generally infinite sums over, separable solutions like that. And the best way to do it is to do an example. I know, how about if we do example 3.3 from the book? And the book has additional examples, which I ought to go over. I'm not going to go over every single one of them in here, just this one, and then there's other ones to look at. So this one says that we've got two infinite grounded metal plates lying parallel to the xz plane and separated by a distance a, and they go off to infinity, except on one side they're cut off, and there's a strip there that has a known potential on it, and our job is to basically figure out what's the potential everywhere. Implicitly, that would let you find the electric field everywhere. So, two infinite, I know that's infinity, but I don't care. Infinite grounded metal plates lie parallel to xz plane, one at y equals 0, the other at y equals a. And one on the left end, not B1, sorry, the left end at x equals 0 is closed off with an infinite strip. I always like these infinite planes and infinite strips and all that, you know. I'd like somebody to build one of these for me sometime. But anyway, closed off with an infinite strip. Insulated from the two plates. So maybe it's a piece of rubber, basically, and so there's no charge going to flow from the strip to the plates. Insulated from the two plates and maintained at a specific potential, which is a function of y. on the strip v naught, v is v naught of y, some known function of y. Name your function of y, and we'll be happy with it. Okay, so our problem, find the potential inside this slot. So we should draw us a pretty picture here. All right. So I drew a nice picture in my notes. I hope I can do a good job again. I was proud of my picture in my notes here. So here's the strip. There, it's the insulated strip. And now that's the z-axis, and here are the x and the y-axes. So the one sticking out is the z-axis this time. And so we make a little drawing where we make the edges crinkly to kind of say, it's going on forever, and we're just showing part of it. And not too bad. So it's y equals a for one of the planes, y equals 0 for the other. These metal planes stretch off to infinity parallel to the xz plane, and there's this insulated strip that goes to infinity. From 0 to a, connecting the two ends along the YZ plane. Okay, everybody get the picture there? See what we're doing? Do I have happiness and joy? Okay. There you go. And you know, anybody can feel free to do what I just did.
Because they're not in a set position.
Yeah, that's right. Oh my God. I feel like I should do this for everyone now, because if I do it for Chris, you know, I don't want to have other people feel like I don't like it. So.
Oh, wait, don't put it right behind Corey. He's going to bump into it.
Corey's a highly competent individual. I trust that he would.
Did he miss his first?
Normally.
Yes.
And then when they trip and fall,
Yeah.
you're going to get sued.
All right.
Thank you, Dr.
Well, you're welcome. Yay, V is independent of Z, right? Nothing depends on Z here, so this is a two-dimensional problem. In reality, that's why we like this infinity business here. It's really a two-dimensional problem. You just need to solve in the xy plane, basically, and then continue that forward along the z-axis to plus and minus infinity. And so all we really need to solve then is the two-dimensional Laplace's equation. E squared v dx squared, well, second partial of v with respect to x, plus second partial of v with respect to y has to be 0. That's what we have to solve inside the slot between the two plates because there's no charge in there. And so, therefore, the potential satisfies Laplace's equation, and our job is to find a solution which satisfies the boundary conditions. That's what it comes down to. You're looking at me funny.
You just want to look funny.
Okay. All right. I should be used to this, however.
Yes.
I just want to be sure you're not looking at me like, does he realize he's got a, thing sticking out of his head or something like that?
I already checked for that.
You already checked for that, thank you.
No antennae sticking out.
No antennae, that's right, yes. I keep them in I keep them in when there's company. Alrighty. Oh, we got some BCs here, some boundary conditions. Boundary conditions are, well, these guys are both grounded, right? Those are both grounded, so therefore V is 0 on both of those planes. So V is equal to 0 when Y is equal to 0 or A. Those are boundary conditions. Another boundary condition is that V is equal to V naught of Y when X is equal to 0 in the slot. That's the insulating strip that's maintained at some fixed known potential as a function of Y. And the other boundary condition, which is the one you have to always remind yourself to think about, is that V goes to 0 as X goes to infinity. In other words, if you go infinitely far along the X-axis here, the potential ought to go to 0. Way, way, way out there. It's like there's a conductor at infinity where the potential goes to 0 if you will. Okay? This is our quest to solve Laplace's equation with these boundary conditions. And because we want our variables to be friendless, we write the solution. We assume that we can find solutions of the form x of x, y of y. So big X and big Y are functions that only depend on x and only depend on y respectively. We don't expect the final solution to just have this form, but again, we're going to get solutions of that form that satisfy most of the boundary conditions. And then we're going to use an infinite series to satisfy the boundary condition on the far left here. And that might seem rather vague at first, but you know, it's learned by doing. So we'll just go for it here. So if I take the second partial of this function with respect to x, then what happens to y in that case? In other words, if I want to take the second partial with respect to x of the quantity, x is a function of x, y is a function of y, what does that become? Y of y is treated as a constant here, so that's just going to be y of y multiplied by, well now x only depends on one, it's a problem, capital X only depends on one variable, x, so when you take a partial derivative of something that only has one variable in it, it's just an ordinary derivative in that case. So in other words, you get y of y times d squared x dx squared when you take that derivative. And so therefore Laplace's equation becomes y d squared x dx squared, d squared big X d little x squared, plus x d squared big Y d little y squared equals 0. If we've got a separable solution, then this is equivalent to, this is Laplace's equation for our separable solution there. Any questions so far? I'm taking a dramatic pause because I see pencils still moving. So the next thing to do, because we want to separate the variables, is divide through by v equals xy. Divide through by v equals xy, and then it turns into 1 over big X d squared big X d little x squared plus 1 over big Y d squared big Y d little y squared is equal to 0. And here we've achieved the separation because, in other words, now we've written it as a sum of a term that only depends on x and a term that only depends on y. So just for a moment, we're going to stop calling it this in a second, but just for a moment, call that first term f of x, and call the second term g of y. The idea here is those things have to add up to 0, or in other words, their sum is constant everywhere, namely equal to 0, and what that implies is that each of the terms must individually be constant, must actually not depend on anything, must be constant. And as your author notes, this is a simple concept, and yet it's one that is somehow elusive. In other words, it's the kind of thing where it's simple, and yet it's something that people get confused about. So, think about this very carefully. Think about this argument. Both terms must, in fact, be constants. We certainly know this one only depends on x, this one only depends on y, but in fact, they both have to be constants. Why? Well, we've got f of x plus g of y has to be 0. Suppose we hold y fixed, keep y constant, and vary x. Keep one of the variables constant and vary the other one. So let's say it's y that we're holding fixed, and we're varying x. If f of x were not a constant, then as we did this, this operation, f of x plus g of y, would change. But it can't, because it's supposed to always add up to 0. Right, that's the idea. Fix yourself at some fixed value of y, move parallel to the x-axis. Since we're keeping a fixed value of y, the value of g isn't changing because we're staying at a fixed y, but we're changing the value of x. So if f of x were a variable, were variable, wasn't staying constant, then f of x plus g of y would be changing, but f of x plus g of y has to add up to 0 at every point, so f of x can't actually be changing, so f of x has to be a constant. Of course, you can, okay, it is no longer true that Nolan doesn't have a cell phone, apparently. And so, having newly acquired a cell phone, she's not used to turning it off during classes. All right. So, anyway, you could also flip the argument around. You could, and here I put no phone number when I registered you for the conference. I didn't know that. All right. So now you can be reached in emergencies and so forth. That's very convenient. Anyway, okay, I've embarrassed her enough. But, yeah. You could flip it around. You could fix x and vary y and make the same argument. So from that pair of arguments, we see that both f of x and g of y have to be constants. They cannot vary. Yes?
What if they just went up and down in the same proportion so that they were always equal to 0?
See, that's the thing. Is at first you might think you could do that, but here's the xy plane here. Here's some location, all right, in the xy plane. So here's some point. Notice what I'm saying to do here is we're going to hold y fixed and vary x. So we'll start at this point right here, we'll hold y fixed and vary x. So we're going to move along that line, right? That's the idea. We're going to move along that line. So the only thing that's varying is x along that line. We're not varying y, so g of y isn't changing because we're not varying y. If we're varying x and f of x is changing, then it would have to be true that f of x plus g of y was changing as we moved along this line, because g of y certainly isn't. So if f of x is changing, their sum is changing, but their sum doesn't change. Their sum always adds up to 0. Yes?
I think what he was saying was, what if you took the case where you did the full multiple constant, you let f of x go up by 5 and g of x go down by 5?
Yeah, and I was like, what if I went like that?
Exactly. Or whatever.
Well,
I know it's just an exception to the rule.
no, but right, no, I mean, you know, so the point would be that you could certainly do that, but that's not going to help you make this argument. So in other words, at any point, I can make this argument that I just made. I could start at this point and go this way and go this way and decide that f of x didn't change along. You know, what we've shown is that f of x doesn't change along this line, right? But I could use this point and I show then that f of x doesn't change along this line, or this point and show that f of x doesn't change along this line. I can take any point and show that f of x doesn't change along a horizontal line through it. Similarly, I can take any point and show that g of y doesn't change along a vertical line through that. Since I can do that for every single point on the plane, then it follows that, yeah, it just has to be constant everywhere.
So this is not a problem with the uniqueness theorem. Like if there are two different situations that could work, but clearly we're not pulling it here, but I'm just saying.
Right, well see but that's the thing, when you know, with the uniqueness theorem, right, that's kind of the question is, are there two different situations that could work? So in the proof, notice what we did in the uniqueness theorem is we assumed there were two and showed they had to be equal to one another. Now there are physical situations where there are multiple solutions. Your author mentions one. Consider, you know, one of those jars of spaghetti where it's one of those button tops, so that it says, you know, do not purchase if the button is up, because as soon as you open it, the vacuum seal goes away and it goes, you know, it pops up again. Well, that lid then has two different stable configurations. So there are physical situations where multiple solutions work, but Laplace's equation and Poisson's equation is not one of them, is what it comes down to. There, the solutions are, in fact, unique. And there you have it, basically. Part of that, you know, is related to the fact that we're talking about electrostatics here. In other words, we don't have anything varying with time. You know, with the lid, it depends on the history, you know, of the lid. In other words, did you evacuate the jar and then attach the lid to it? Or did you not evacuate the jar, take the air out and attach the lid to it? It depends on its history, how it's configured there. With electrostatics, the history doesn't matter. All that matters is where the charges are now. And so from that, we kind of expect there ought to be a unique solution. That doesn't prove it, but in other words, often when you've got a situation in physics where there's multiple solutions, it turns out which one happens depends on the history. Depends on how the system got to where it was. Okay? So, everybody happy with the argument there that these guys both have to be constants? And it's the kind of thing where, think about it, you know, think about it again later as you're walking across the street. Pay attention, no, as you're walking down the street, pay attention as you're crossing the street, and then start thinking about it again. All right? So, given that those guys both have to be constants, it follows that whatever one is, the other is minus that, because they're adding up to 0. So we've got to have that 1 over x, d squared x dx squared is equal to some constant c1, 1 over y, d squared y dy squared is some constant c2, and c1 plus c2 has to add up to 0. And here, it turns out we need C1 to be greater than 0, C2 to be less than 0. In general, you got to try all the possibilities. Here, having pre-digested the possibilities, we'll just say it turns out you want C1 to be greater than 0, C2 to be less than 0, and as we go through it, it'll be clear why that turns out to be the case. It's because it needs to do that to satisfy the boundary conditions. So we'll just call C1 k squared and C2 minus k squared, which might suggest to you kind of we're going to get sine functions out of this somehow because k's like to show up in sine functions. That is in fact the case. So our two equations are 1 over x d squared x dx squared is equal to, whoops, that's not what I meant to say. D squared x dx squared is equal to k squared x, Dr. Harmon made it in his notes, because I have 1 over x d squared x dx squared is k squared x. I meant to multiply through by x. So it's 1 over, it's just d squared x dx squared is equal to k squared x is one of the equations. So scratch out the 1 over x in front of that in my notes if you're following there on page 69. And d squared y dy squared is equal to minus k squared y. So the first equation says I need a function whose second derivative is k squared times the function itself. So what sort of functions have that property, that the second derivative is a constant times the function itself? No, that's what's exponential, right? You're almost right. That'll be the next one, right? Exponentials do that because the derivative of e to the x is e to the x. So you can take derivatives all day, and e to the x just keeps turning into e to the x. Well, we want something a little different because it's got to turn into k squared times e to the x. So what do we need to do? What can I do to get it k squared times e? Of course, you got the note, you just glance at it. So don't. Okay.
Just make it e to the constant.
Yeah, e to the, and what constant would that be?
The root of the one that you want.
Yeah, so I need the square root of k squared being the constant, or in other words, just k. Hey, that's why we make it k squared. So it'll be e to the kx, differentiate once, that's k e to the kx, differentiate twice, that's k squared e to the kx. There's another one that works too, which we expect. It's a second order ordinary differential equation, so there should be two linearly independent solutions, as you will recall from your differential equations class. What's the other Li solution? E to the kx and e to the minus kx, right? Because e to the minus kx gives you minus k e to the minus kx. Differentiate again, you get minus k times minus k e to the minus kx, or k squared e to the minus kx. Sold for $50. Okay? So, general solution. General solution of the x equation is big X as a function of x is some constant a e to the plus kx plus another constant b e to the minus kx. Oh my God, this is sounding so quantum mechanical, right? You know, it's like we're doing the infinite square well here. We're not, but you know, it's the same kind of stuff that shows up. Because after all, Schrodinger's equation involves the Laplacian, right? So we're going to see Schrodinger. In fact, you know, it's important to remember that the folks that invented quantum mechanics already knew partial differential equations. They'd already done E and M. They'd already seen separable solutions in E and M and so forth. So they had something to go from when they were inventing quantum mechanics. In other words, Schrodinger invented a wave equation for quantum mechanics because he knew about quantization in other contexts, and he thought, okay, I need to get quantization of energy in hydrogen. Wave equations often show quantization, discrete values based on boundary conditions, so maybe that works here too, and voila. He didn't just pull this, you know, completely out of midair. He was working on something, working from a basis there. Oh yeah, quantum mechanics working from a basis, that's almost a fun. Anyway, d squared y dy squared is minus k squared y. Steph, what would the solutions of that look like? Why, sinusoids, yes. There would be sine kx and cosine kx, both twice differentiated, give minus k squared times the original function, because sine goes to cosine goes to minus sine, cosine goes to minus sine goes to minus cosine. So, therefore, for the y equation, we'll have y as a function of y is equal to c sine ky plus d cosine ky as the general solution. So, now we've got boundary conditions to satisfy. So we write our general solution, well, not perfectly, but our v of xy for our separable solution, I should say, not the general solution, is equal to a e to the kx plus b e to the minus kx multiplied by c sine ky plus b cosine ky. C sin e plus d cos. Now it's time for some boundary condition fun. So v goes to 0 as x goes to infinity demands that, well, we've got, in general, two terms we can have here, a e to the kx plus b e to the minus kx. One of these things doesn't belong because it explodes as you go to x equals infinity. And that, of course, would be, which of those two terms? The first one, yeah, that would blow up as you go to infinity. Now, if there was a boundary over here, if there was, say, another conductor over here and the potential is going, then you're going to need both terms in general. But this convenient problem where we get to go off to infinity, we get to demand that a has to be equal to 0, else e to the kx would make it blow up good. We don't want our solution to blow up good. So we make a have to be 0 in order to avoid that. I'll wait a moment for pencils to catch up. And so now, our v of xy separable solution can be written as e to the minus kx c sine ky plus d cosine ky for all we know so far. We don't keep the b around because we can just make we can just absorb it into c and d. You know, what was before bc can become the new c, and what was before bd can become the new d. We just absorb that into the other c prime and d prime. No, because after all, I can call the constants whatever I like.
Yeah, but that's not the same as that.
If you feel better, you can make it like that in your notes. Okay, so now we've got more BCs to apply. B has to be 0 when y equals 0. All right. Well, let's see. Sine k0 is 0. No information there, because then that just gives 0, and so that's not harming, but it's not, you know, it's not telling us anything about c. On the other hand, cosine k0 is 1, right? So at y equals 0, this becomes e to the minus k0, which of course is also 1. It becomes 1 times d times 1, right? So implies 0 equals 1 times d times 1. Okay, solve that for d. What do you get? Yeah, you get duh. So d has to be 0.
Did you, sorry, stupid question, but did you also say that x equals 0? Y equals 0 and x?
No, just y equals 0. Yeah, because the boundary condition here is that when y is equal to 0, no matter what x and z are, when y is equal to 0, the function is equal to 0. So, yeah, I'm sorry, I did say x was 0
I
here.
was like,
So,
all right.
yeah, you're right, Steph. Actually, thank you. Yes, 0 equals actually e to the minus. No, so you made a good point.
Yeah.
E to the minus kx times d times 1, but that still means e is 0.
Yeah.
D is
Sorry, I
0,
didn't mean like.
yes. No, that was actually a good point. Thank you. Yeah, thank you.
I just didn't know if x needed to.
Right, it did not need to be, so I'm glad you said that, yeah. I was goofing, you have set me back on the path of righteousness. Yes, thus saith the step. Okay, so d is in fact 0 because e to the minus kx d has to be 0. That means d is 0 because x could be anything. So therefore, okay. Our coefficients are falling like flies, which is a happy thing. B equals 0 when y equals a now says, excuse me, that, so you know, so then now after we got rid of c, we're just left with e to the minus kx times, after we got rid of d, stop it, then we've got c e to the minus kx sine ky is what our function would be. So c e to the minus ka, stop it, kx sine ka has to be equal to 0, right? Is that right? Did I screw that up? Let's see what's happening. Okay, right? So in other words, again, since x could be anything, in particular, we need sine ka to be equal to 0. And, well, when is the sine function equal to 0? When its argument is, well, 0 works, right? What else works? Multiples of pi, yeah. So k times a has to be, well, we don't want it to be 0 because then the whole solution is just 0 everywhere. And that would be the solution if the strip was maintained at potential 0 everywhere, but that's probably not the situation we're interested in here. So we want Ka to be pi, 2 pi, 3 pi, dot. Or in other words, K should be n pi over A for n equals 1, 2, 3, dot, integers. Now you might say, but minus pi, and minus 2 pi, and minus 3 pi, and so forth work. So how come we don't include negative integers too? Why don't we include negative integers too? Well, what is a way to rewrite the sign of, say, minus n pi over a, where n is some positive integer? Yeah, sine of minus theta is minus the sine of theta, right? So this would just become minus sine of n pi over a. And that's not a genuinely new solution. In other words, if I'm going to have ultimately we're going to sum over solutions here, and if I have a solution which there's one which is sine of 3 pi over a, and then I also want to include sine of minus 3 pi over a, well, one of those is just minus the other one, so the coefficient could take on that role. In other words, if I put in a negative number here, then I could just make c go to minus c and I'd have the same solution back. So just changing the sign of the solution doesn't really make it a genuinely new solution. Right? Does that make sense? Not? Yes? No? Yes? No? I don't see universal waving heads like this for appreciating that that is the case. Is that true, or is it just because people aren't doing anything?
Interact with the sign.
What's that?
So we can interact with the sign.
You could interact with the sign? What does that mean?
I don't know.
You don't know.
Just to become more.
Just to become, right, yes, okay. In other words, if v of x, so we got v of xy, then out of all this is going to be c e to the minus, and then we've got k has to be n pi over a. E to the minus n pi over a x times sine of n, oops, that's supposed to have an x on it. Sine n pi over a x. If n goes to minus n, that just flips the sign of v of x and y. But ultimately, I'm going to add a bunch of these together with coefficients in front. And so, if I just flip the sign of v of x and y, I could also just let c go to minus c, and I'd be back where I was again. In general, you've got a bunch of things you're going to add together with coefficients out front. If you've got negative terms that are identical, if you've got solutions which are just minus other solutions, the coefficients take care of that. They're not genuinely new solutions when you're going to add them together. And I still see people kind of looking at me like, huh? But I can't tell if that's genuine, huh? Or just not being willing to interact. What do you think, dear?
What about the e to the x, the kx term? Because you're gonna, I think that's more.
Okay, now you got me in trouble. Yeah,
Yeah,
that's a
I
good
did.
point. Let's see. Right. Damn it. No,
I'm sorry.
Right, so, man, I hate it when that happens. Let's see. Oh, no, that's actually another way to look at it, because if that became negative, right? So actually, yeah, if that became negative, what would happen to this exponential as we went to infinity? It would explode, yeah. So actually, that's another way to. That's actually a good way to. Yeah, that's. So you got to exclude negative ones just because that would make the exponential blow up. Oh, that's even better.
Yeah.
I should ask you things more often, basically. See, actually, here, why don't you just teach the class? Yeah. So that's even better. Yeah, we have to throw away the minus ones because otherwise the exponential would blow up. Of course, then you could say, oh, but then you could just put in. That doesn't, well, but then the thing would be though, because then you could throw in the other exponential. You could put in the e to the n pi over it.
But
Yeah, but we already threw it out because we were assuming that the coefficient was negative. Anyway, by hook or by crook, it's got to be c times e to the negative exponential times e to the, this. Now you could think you could, okay, well, why can't I just put a negative thing right there? This would still be a solution, right? If I put a minus sign there, this would still be a solution, right? But we throw away the solutions that would have a minus sign right there. They're still solutions because they're just minus the solutions that we're keeping. And making minus the solution isn't anything new because you're multiplying by a c, which can also be positive or negative. So it's not anything new. Yes?
Why is the sign of x? What is that?
Sign of,
Well, it's like.
it's y. Good Lord.
Yay.
Because it's y. Yes, thank you
Down there.
for saying that. Yes, thank you. Yes.
Yay.
Yes, very good. I want you to do stuff like that because otherwise people are like, what the hell are you doing? Yeah. Why? Thank you. Yes.
If you made n go the negative numbers, wouldn't it cancel out in our sum?
Yeah, essentially, the idea would be, well,
Because if it was just a negative of the sign, then
well, you could use different coefficients, but yeah, I mean, Three sine theta is equal to 4 sine theta plus 1 times the sine of minus theta, right? Isn't that correct? 3 sine theta is 4 sine theta plus 1 times the sine of minus theta. So in other words, putting in the sign minus theta term isn't giving you anything new, because if I just wanted that, sure, I could break it up into a sine of theta and a sine of minus theta, but why would I do that? You know, there's no point. So we're going to add a bunch of solutions. I feel like I'm making too much of this here, but we're just going to add a bunch of solutions together, and so we don't need the ones that have minuses. We just throw them away. They're nothing fundamentally new, because you can just make the coefficient negative and get those, and so.
Just don't do it.
All right. Yeah.
Yeah, end of story. How about we?
Yeah. End of
do
story.
not.
Right. Just don't. Yeah. Just don't need them. Got a better way to say it?
No.
No. Okay. All right. Wow, I did really well on page 70 there. Then when I wrote v of x, y, I flipped the x's and the y's.
Oh, yeah, fix that.
Yeah, I definitely have to fix that, yes. All right. I knew what I meant. Yeah. So that's the disadvantage of putting your notes out, because I would just catch that if I were just doing it and then not even write it and not even mention that it was like that in my notes. All right, so v of x, y, our separable solutions have the form c sub n e to the minus n pi x over a times sine of n pi y over a for n equals 1, 2, 3, blah, 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 blah. Yeah, I'm allowed. We've got an infinite set of them. And they all satisfy 3 of the 4 BCs. They'll satisfy 3 of the 4 boundary conditions, namely y equals 0 boundary condition, y equals a boundary condition, x goes to infinity boundary condition. What we haven't accounted for yet is the boundary condition over here on the left end, on the insulating strip. Excuse me. So, how are we going to do that? Well, what we're going to do is use the sum. Laplace's equation is linear. The sum of 2 solutions of Laplace's equation is also a solution of Laplace's equation. In other words, if grad squared v1 is equal to 0, and grad squared v2 is equal to 0, then grad squared of v1 plus v2 is grad squared of v1 plus grad squared of v2 is equal to 0 plus 0, which adds up to 0. So the sum of solutions of Laplace's equation is also a solution to Laplace's equation. So that means that any sum of solutions of this form of Laplace's equation is also a solution of Laplace's equation. So in other words, v of x, y, being the sum from n equals 1 to infinity of Cn e to the minus n pi x over a sine n pi y over a is a solution of Laplace's equation, because each term is a solution of Laplace's equation. So after you go chat with Linné, we'll apply that principle to actually solving our original problem. so I'm going to try one more time with the why we throw away the solutions with negative n here. We're going to make a sum of all these solutions here, right? And so just like before, I said that, well, you know, the sine of 3 theta, you could also write that as 3 times the sine of theta. Well, that's 4 sine theta plus 1 times sine of minus theta. If we're determining these coefficients and we kept negative n's in here, they wouldn't be unique anymore, because any sine of theta term could be, or sine of 2 theta, sine of 3 theta, could be written as some arbitrary combination of sine of 3 theta plus something times sine of 3 theta plus something times sine of minus 3 theta, and so forth. So if you want these coefficients to be uniquely determined, you can't have negative n values. Or you can't have positive n values. In other words, you could agree, we're only going to keep the negative n values, or we're only going to keep the positive n values, or you could be really weird and say we're going to use positive odd n values and negative even n values, you know, and then you're an idiot. Or for prime n values, we'll make positives, and then if it's not prime, it'll be negative. You can do something stupid like that, but the point is, you only want one of them for each n, and so we just say, okay, we'll make the positive n for each one, as opposed to some other possibility. All right, so we have one more boundary condition to satisfy, and that is the one at the strip on the edge here. Or in other words, that is the one at x equals 0. Here we do finally have to plug in x equals 0. So with our solution there, which is written as that infinite sum we're guessing, we're saying, okay, let's assume we can write the solution as this infinite sum, whatever it may be, this infinite series. Then for the final BC, we have v of 0 comma y. In other words, we're putting x equals 0, an arbitrary value of y, understood between 0 and a, is equal to the sum from n equals 1 to infinity of c sub n, and then we got e to the minus k0, e to the minus n, e to the minus n pi x over a is 0 at x equals 0. Stop at 1 at x equals 0. X is 0. Shut up. All right, that term, the exponential is 1. Yeah, so this is just the week. Anyway, sine n pi y over a, the exponential is 1, so we get sine n pi y over a is equal to the given function, v naught is a function of y. So, the question is, can we accomplish this? Can we add that infinite number of sine terms together to produce some arbitrary function, v naught of y, where arbitrary means the physicist's arbitrary, finite number of discontinuities type of thing, you know, not arbitrary where it could be, not continuous, but arbitrary in the physicist's sense. Can we do that? Have you seen this sort of beast before? What is that? Have you seen this sort of beast before? I have some function and I want to write it as a sum over an infinite number of sinusoidal terms. That's called a... Yeah! Yes, Fourier series. That's a Fourier series. That's a Fourier series. We got us a Fourier series. And in fact, in particular, it's the Fourier sine series that we've got here. So how do you find the coefficients in a Fourier series? Well, we exploit what we call the orthogonality of the sine functions. We can find the Cn by exploiting orthogonality. property that the integral from 0 to a of sine n pi y over a times sine m pi y over a is equal to 0 when m and n are not equal to one another, and to a over 2 when m and n are equal to one another. Or another way to write that, it would be a over 2 times the Kronecker delta mn. Remember, the Kronecker delta is this little beast that's 0 when its two subscripts are not equal, and 1 when its two subscripts are equal to one another. So we call this the orthogonality property. Two functions, f of x and g of x, are said to be orthogonal if their integral, integrate one with the other, gives 0. So if that integral is 0, then we say orthogal. It's orthogal. Wearing her cape, she's the superheroine. Orthogonal. Really, I should say orthogonal means that integral is 0. Why do we call that orthogonal? Why do we say the two functions are orthogonal? If f of x times g of x integrates to 0, why do we say they're orthogonal? Yeah, it normally does, right? If the dot product is 0, two vectors are orthogonal to one another, right? So if I took a dot product of two vectors, f dot g, well, that would be you multiply the components together and add them, right? So I'd sum over I of figi. Well, notice that could be in any number of dimensions. It could be in 36 dimensions. You could have 36 perpendicular axes. Have fun drawing them, but in principle, you could have a 36-dimensional space, so every vector had 36 components. And if two vectors were perpendicular to one another, orthogonal to one another, then if you added up the products of the 36 components and they added up to 0, they'd be orthogonal to each other. Well, note the similarity between this expression, sum of the figi, sum of the components, and this expression, integral of f of x, g of x dx. In both cases, you can think of yourself as multiplying components together and adding them. In other words, you think of a vector like f of x as living in an infinite dimensional space where there's one dimension for every value of x. So every value of x is a dimension, every value of x gets an axis in that space, if you will. So there's an infinite number of axes. It's an infinite dimensional space. And the components of the function are the values of f of x. And similarly, g lives in that space too, and the values of g at each value of x is a component of g in that infinite dimensional space. And so we just multiply all the components together and add them up, and if it adds up to 0, the two functions are perpendicular to one another in that infinite dimensional space. If you've had quantum mechanics, this should remind you that we say that if we use a ket to represent f, then we say that f of x is the projection of f along the bra x, like that. Remember that business? So this is coming from that idea. Now in quantum mechanics, you would use the definition of orthogonality where you make the star of one of them. In a complex space, orthogonality is f of x g star of x dx equals to 0. But if we're in a real space, complex conjugate of a real function is the function itself again. So we needed to make that distinction. So we're saying they're orthogonal to one another because it's like an infinite dimensional dot product, basically. Does that make sense? See what I'm getting at? Does that make sense there. It's not really crucial. Yeah, that's what I like, yeah. Happiness and joy. Yay, Dr. Harmon, yay, we're so happy and joyful. Yay. It's actually not particularly necessary here. I just kind of want to point out that's why it's called orthogonal. Because it's like their infinite dimensional dot product is 0, if you will. So, exploiting orthogonality, what we do is multiply both sides by sine m pi y over a and integrate. So the sum from 1 to infinity of Cn times the integral from 0 to a of sine m pi y over a sine n pi y over a dy, that's the left-hand side, multiplied by sine m pi y over a integrated, is equal to, same operation on the right-hand side, is equal to the integral from 0 to a of sine m pi y over a d naught of y dy. Just multiply both sides of this expression by sine m pi y over a, integrated between 0 and a. Now, this integral on the right side, well, actually it's an infinite number of integrals, they are equal to a over 2 delta mn. So we've got the sum of Cn times a over 2 delta mn is equal to integral from 0 to a of sine pi y over a d naught of y dy. And if I evaluate that sum on the left there, what do I get? Well, the Kronecker delta is 0 except when m is equal to n, in which case it is 1. What's that? No, not any, no.
Fix your
For your limits.
My limits?
summation.
Oh, sorry, yeah, 1 to infinity, thank you, yeah. All right. So I add up all the values of n of Cn, a over 2 delta mn. Delta mn is 0 for every value of m except for the one where m is equal to n. So you just get Cm times a over 2, right? That's the only thing that lives out of this summation. So you get a over 2 Cm equals the integral from 0 to a of sine m pi y over a b naught of y dy.
Did you fix page 72?
I did, yeah, actually. And so therefore, C sub n is equal to 2 over a times the integral from 0 to a of sine n pi y over a d naught of y dy. Box around that, because that's a very important formula. Notice that I just changed the name from m back to n again, right? Because it doesn't matter. This could have, you know, Cm sine m pi y, I could have called it C sub potato chip, sine potato chip pi y. It doesn't matter what you call the variable, so I just named it back to n again, basically. So C sub n is 2 over a, integral from 0 to a of sine n pi y over a v naught of y dy. If this were quantum mechanics, we would have made the functions root 2 over a times so that they would have been normalized, and then it would have just been the normalized function times. But anyway, yes?
I don't know if you already said this or not, but you forget the A over 2 is
Did I? Oh, I was, okay, oh crap. You know, maybe I just didn't rescan it, because I've got it in my note, like, let me show you what I've got here. Oh, yeah, I must have fixed it. Yeah, I think I might have even rescanned it, I'm not sure. But yes, in my original notes, yeah, it is supposed to say 2 over 8
Online,
there.
it doesn't.
It does not, okay,
It's
so.
okay.
Yeah, right, but yeah, there should be a 2 over A in there, indeed, yes.
2 over A.
Yeah, right here. Yeah, 2 over A at integral, yes, absolutely. Okay, so notice the Kronecker delta acts a lot like the delta function does. In other words, it picks out a single value, namely the one where its arguments are equal. Delta function does the same thing. If you integrate f of x delta of x minus a dx, you get f of a. The only term that lives is the one where x equals a. The Kronecker delta is to a sum what the Dirac delta is to an integral. In fact, it really historically went the other way around. The reason it's called the Dirac delta function is by analysis. It does for integrals what the Kronecker delta does for sums. The Kronecker delta came first. Okay? So, the solution to the problem then, you can write the general solution as just then that g of x, y is that summation, n equals 1 to infinity, of Cn e to the minus n pi x over a sine n pi y over a, where Cn equals that. That's the general solution. Question? Now, of course, for a specific v naught of y, you actually have to evaluate the C sub n, and you actually do it. And at first, it looks like, I've got an infinite number of integrals to do. But typically, what you find is you can just do it generically once and get the coefficients as a function of n. You don't actually have to do an infinite number of integrals here. They're passing notes. So, for example,
Sure.
what?
Oh,
What?
I was going to say, you want to read them out loud?
Huh?
You said passing notes.
Do you want to read it out loud? And then
Oh yeah, you want to read it out loud and you say, for example, right? Yeah, right. Yeah. That'd be kind of amusing, wouldn't it? Yes. For example, now I lost where the hell I am. Let's see, for example, here, why don't you read that for me, Pastor? For example, suppose v naught of y equals a constant equals v naught. Suppose that's what we're trying to satisfy there. Then in that case, C sub n would be equal to 2v naught over a times the integral from 0 to a of sine n pi y over a dy. And if you use Mathematica for that, I'm kidding. Equals 2v naught over a times minus a over n pi cosine n pi y over a evaluated between 0 and a. Equals 2v naught over n pi times 1 minus cosine n pi, 1 minus cosine n pi, but that's probably better written as 0 for even numbered terms and 4v naught over n pi for odd numbered terms, because if n is even, then you get cosine of 2 pi or 4 pi or whatever, which is equal to 1. So you get 1 minus 1 equals 0 when n is even. When n is odd, the cosine of an odd integer times pi is minus 1. So you get 1 minus minus 1 is 2, times 2 is 4 v naught over n pi. So it's probably better to write that as 0 for all the even terms, 4 v naught over n pi for all the odd terms. And so then you can write the infinite series. You can put that in for your infinite series. For any finite number of terms, you get an approximation to the solution. Turns out in this case the series can be summed. It's like a sinh function or something like that, but I didn't. So that's in the book. I didn't even bother writing it here, but because in general you can't sum the series explicitly. So here you'd write v of x and y is 4v naught over pi times the sum over n odd of 1 over n times e to the minus n pi x over a times sine n pi y over a. So that's the solution in that particular case of the infinite strip being held at a fixed potential v naught. And it's a sum from 1 to infinity, so in practice, if the series can't be explicitly summed to some analytical form, you have to take finite approximations. You might sum out to n equals 19 or something like that. This is the sort of thing where you can ask Mathematica to plot better and better approximations as you keep more and more values of n. But the happy thing is, notice that no, we don't, typically you don't actually have to do an infinite number of integrals, one for each n. You just put in n generically and you get something out that gives you c sub n generically. Okay? Questions, comments, observations? Well, that was fun. And you know what? If Cartesian coordinates are fun, spherical coordinates are going to be even funner. Funner is the word I'm looking for. Yes. Funner is the pseudo word that I'm looking for.
Is that the word of the day?
The word of the day is funner. For example, as wives go, chunner is funner.
That's cute.
Why, you're my funner, chunner, hunter. Or are you my funny, chunny, honey? Or I don't know.
You can stop now.
Yeah, I'll stop now. We do not need to see that.
No, we don't.
Right. Spherical coordinates. Sadly, we're going to assume azimuthal symmetry, so we won't get to use full-blown spherical harmonics.
Dang it.
But we will get to use Legendre polynomials. So all is not lost. That's right.
I'm so
We just throw away
Can we what?
We just throw away azimuthal symmetry and just like
Yeah.
go all out.
Just yeah, right. Yeah.
It makes me happy.
Yeah, this totally looks sunshine.
Oh yeah.
Yeah, these are really sweet.
Oh, it's a nice one, isn't it?
Yeah.
There you go. In spherical coordinates, Laplace's equation, of course, as everybody has memorized by now, 1 over r squared partial with respect to r of r squared partial of v with respect to r, plus 1 over r squared sine theta times partial with respect to theta of sine theta partial of v with respect to theta plus 1 over r squared sine squared theta times the partial, second partial of v with respect to v, adding up to 0. That's a nice one. But on the other hand, you know, if you take in quantum, you've seen this beast because the hydrogen atom, you use spherical coordinates, that's the Laplacian in spherical coordinates. And so this isn't something, if you've taken quantum, you've never seen before. On the other hand, if you haven't taken quantum, then when you take quantum, you can say, I've seen this before, right? Either way, there's happiness and joy to be had here. It's important.
I'm not. I'm not excited for I'm not. So that's fine.
Sadly, we're going to assume v doesn't depend on phi, so that this term will go away. And so the third term goes bye-bye. And we want to separate our variables. So we will assume that we can write d of r and theta is equal to some big R of r, and then something you don't see much, capital theta of theta, circle with an h in it, so to speak, a real flat h. So r of r, theta of theta, I guess you see that you're dealing with fraternities or sororities potentially, but I don't have many occasions to write capital Greek thetas. So we plug that into our equation where the third term has gone bye-bye, and we'll get then that theta times 1 over r squared ordinary derivative with respect to r of r squared d big R dr plus big R times 1 over r squared sine theta times d d theta of sine theta dv d theta is equal to 0. In other words, we've done what we did before, plug that in. When you're differentiating with respect to r, theta doesn't care, so it flies outside. When you're differentiating with respect to theta, r doesn't care, so it flies outside. And then to achieve true happiness of variable separation, divide through by v equals r theta. And what we'll get is 1 over big R times d dr of r squared dr dr plus 1 over big theta, 1 over sine theta, d d theta of sine theta, d big theta, d theta is equal to 0, where we've also multiplied through by little r squared since it's equal to 0 on the other side, so we can just multiply through by little r squared and get rid of that. So here's the equation that gets the box. And of course, as everybody knows, the solutions of that are Legendre polynomials. Duh. That's right.
Come on. Who doesn't have Legendre polynomials memorized?
Oh, come on, yeah, really. I mean, if if you didn't get them in kindergarten, at least by first grade.
Seriously.
Yeah,
Flashcards.
Doctor,
that's right. Yes?
when you're pulling the data, or big data MDR out
Mhm.
of that last term, the
Yeah.
sign,
Mhm.
is it supposed to be D data? Yeah.
Your V needs to change. You have-
Oh, yeah, sorry, yeah.
No, the other
Yeah,
one.
this is supposed to be a d theta, thank you. Yeah, absolutely, thank you. I multiplied through,
Okay, gotcha.
since zero's over there, so,
I didn't see that, I was like.
yeah.
What?
So I said, KISS 0 little r squared, and it went away for us as a result. All right? So this is our quest, to find separable solutions by using that equation right there. And happily, we're just going to say, and the solution is, for the most part, but then you can easily check that those are the solutions. So, again, same argument as before, both terms must equal constants by the same argument. And because smart people already have done this problem before, we're going to make a really good choice of what we call the constants. So naturally, we'll call them L times L plus 1 and minus L times L plus 1. That's how we'll call the constants. We'll call them L times L plus 1 and minus L times L plus 1. Where L turns out to be an integer greater than 0. Remind you of anything from quantum mechanics, those of you who have had quantum mechanics? Nope, she
Actually, I
said.
was just saying, I know that's a quantum number, but I can't remember what.
It's the quantum number that represents,
It's not spin.
yeah, it's the orbital angular momentum
Oh, that's
quantum
right.
number. Yeah, orbital angular momentum quantum number. In the quantum mechanical problem, this shows up as the orbital angular momentum quantum number. In other words, remember, L squared is equal to L plus 1 h bar squared in quantum mechanics. But, again, these, that's right. Yeah, it's always helpful if you haven't had something to get an analogy with it. I remember when I was in high school trying to teach myself circuits, and so I get this electronics book, and they keep using analogies with water flowing through hoses, and I'm thinking this isn't helpful because I don't have any intuition for water flowing through hoses. So quit trying to make me understand voltage drops in terms of pressure drops through hoses. I don't know pressure drops through hoses. So, I agree.
Did your family not use hoses?
I mean,
No, no, we didn't use hoses. No.
Wait,
Okay.
no.
So,
You're right.
Yeah, see, that's the problem.
I feel like it's much more reasonable for,
When you're giving an analogy, quantum mechanics is really bad to give an analogy.
much more reasonable to assume that someone should understand a little bit about water flowing through a hose than quantum mechanics.
no, that's not reasonable at all. Don't give me that.
Not certain, no, physics major's not.
Yeah, cut it out.
What's that reason?
Water, hose.
No, he says,
Quantum mechanics.
yeah.
Exactly.
Now, I think so. An analogy with quantum mechanics is maybe a little more over the top than an analogy with water.
I feel like for most people, it's more reasonable to assume they know a little bit about water through a hose than not assuming that.
Well, look, if you want to develop quantum mechanical intuition, all you have to do is walk through a door. That doesn't work.
So,
Oh, yes.
Yeah. All right. Solution. Well, if you haven't had quantum mechanics yet, then just keep this in mind for when you do. Solution of the radial equation, the one for R, is R of R is equal to A R to the Lth power plus plus b divided by r to the l plus 1, where a and b are constants. I leave it to the student to do the trivial action of verifying that. That's easy, you know, geez, you just plug it into the equation and verify that. That 1 over r ddr of r squared dr, where that's r, is equal to 0. That really is trivial. I mean, I'm not joking, it's trivial. to verify that.
Thanks, kidding it for a second.
No, I'm not kidding. I'm not kidding. It's true. I mean, you can differentiate that, right? You know, so it's not hard. So seriously, I really do leave it to the student to verify that.
Gosh.
And the solution to the angular equation. Well, here, showing any individual solution works is trivial. Showing the general formula works is a little less trivial. The solution to the angular equation, remember your halcyon days of elementary
Like
school.
days.
House and house.
That's ice cream. I would like some halcyon dust.
Only if you put a mask on it.
Yes, right, yeah.
House and house.
As every elementary school child knows, the angular equation
Yeah.
has solutions of the form theta of theta is PL of cosine theta. Now, of course, if there were angular dependence here, you would want the associated Legendre function PLM of cosine theta e to the I of phi, which is called the spherical harmonic YLM of theta and phi. Sadly, however, we're not going to use spherical harmonics here. We'll just use PL of cosine theta. PL of cosine theta is PL0 of cosine theta. In other words, the associated Legendre function for m equals 0 is a Legendre polynomial. None of that really matters. I'm just, you know, if you've had quantum, that should be ringing a bell, and so that's why I'm saying that. What's that?
YLMs.
YLMs, that's right, yes, YLMs. Where PL is a Legendre polynomial. A Legendre polynomial. A name that will forever be cursed by students everywhere. But they're really not that bad.
Yeah, we already
That
left.
was like last week. In this class.
I don't remember that at all.
Apparently you don't pay attention. Said halcyon.
I'm looking
Yeah, I did.
at
I said halcyon last week.
And everybody's doing cattle, and then we explained.
Exactly. Beautiful, restful, peaceful. Yeah.
I don't remember this at all.
You don't remember
I'm
that?
going to break it down. I'm looking.
Wow.
Yeah, when did you know?
We were in here. We were in this.
Seriously, I don't remember it either. I don't remember.
Quite the big deal was made of it, as I recall. Yes. Right. I believe, Ben, did you look it up? I don't know.
William, Corey, and I are
Oh,
out.
yeah, you said you thought that it
Everyone,
meant,
yeah.
right, yeah, okay, yeah.
It
Are you being serious right now?
Yes. I've got the DVD, I can show it to you.
Oh, yeah, that's true. We
Yeah, I
have-
turned around, you guys were just now busy.
video evidence.
Let's roll that beautiful people.
It was probably on Thursday,
I'm
I'm
looking.
guessing.
We, I don't know what this was.
You know, you said you know what day it is?
I don't know, I probably wrote it. It's the halcyon days of physical life.
It's true, covering caps. Just started covering caps.
Yeah.
Ah. I don't like that.
Yeah.
What
You
day
hate
did you
the
write that
Rodriguez
on?
formulas.
Thursday?
Guessing Thursday.
The date.
This formula will give you the Legendre polynomials. PL of x is 1 over 2 to the L factorial times the nth derivative of the quantity x squared minus 1 to the nth power. It's a lovely one. So you're like, what is the, why would you, what person would put 1 over 2 to the L factorial in front of it? That's kind of like me, I look at a sea cucumber and think, who ever looked at that and said, I'm going to put that in my mouth? But in this case, there is some logic to it. That's there to ensure that P0 of x is just equal to 1. That makes P0 of x equal to 1 by putting that factor in front there. So notice that we're doing PL of cosine theta, so you have to put in cosine theta for x here, but you generate them using just generically x, and then you plug in cosine theta. So first 6 of them are P0 of x is 1. P1 of x is x. Sadly, it doesn't continue where P2 of x is x squared, but on the other hand, it's not, again, these are the kind of things where people are like, oh, but they're really not that frightening. And in practice, you look the things up is what it comes down to. So P2 of x is 1 over 2, 3x squared plus 1. And, Mathematica, I think there's a function, Legendre P or something. What's that?
Minus or plus?
Minus 1. Like I said, minus 1, yes. Okay, and P3 of x, thank you, P3 of x is equal to 1/2 times 5x cubed minus 3x. And P4 of x is 1/8 of 35x to the 4th minus 30x squared plus 3. And P5 of x is 1/8 of 63x to the 5th minus 70x cubed plus 15x. And on and on and on and on. Something to note is that P sub n of x starts with some constant times x to the nth power. Handy thing to keep in mind. And so in other words, P4 starts with something times x to the 4th, P5 starts with something times x to the 5th, P704 starts with something times x to the 704th power, and so forth. Another thing to notice is that if the subscript is odd, then only odd powers of x appear, and if the subscript is even, only even powers of x appear. Another helpful pattern to remember. And again, yeah, you can get them from the Rodriguez formula. In practice, you look things up. That's what it comes down to. There's tables of these things. Mathematica has built-in tables of these things. And we're doing PL of cosine theta. So for example, P5 of cosine theta is 1/8 of 63 cosine theta to the 5th power minus 70 cosine theta to the 3rd power plus 15 cosine theta. You have to put in cosine theta wherever you see x when you're actually looking at these solutions. Okay. Now, of course, you've all been waiting to jump on me because the angular equation is a second-order ordinary differential equation, and so you're thinking, but Dr. Harmon, you've only written one solution, and of course we all know that every second-order linear equation, or linear differential equation, should have two linearly independent solutions. Dr. Harmon, how come you didn't write another linearly independent solution? And the answer is because we can toss them. The answer is the other Li, linearly independent solution for each L, blows up good. That thing theta equals 0 and or theta equals pi, i.e. the z-axis. They could blow up on the z-axis. So typically, we throw them out because we're not going to be able to satisfy boundary conditions with potentials that blow up on the z-axis. If you had some situation where you had a problem that excluded the z-axis, you might have to include them. Like if you, here, we want the potential inside of a sphere which has two cones cut out at the top and the bottom, meeting at a vertex at the origin. Find the potential inside the sphere. Then you'd need the other solutions, the linearly independent solutions for theta. And there are weird things like, log tan theta kind of stuff like that. Sadly, we're not going to make problems that exclude the z-axis, and so we won't ever need those solutions. So we will disappointedly and dejectedly stick to the Legendre polynomials for the angular solutions. Yes, I know, Corey, it hurts me too, but sometimes you just have to live with little disappointments in life. This can be an important lesson for us all. Okay? So, what that means then is for azimuthal symmetry, which is what we're assuming, no phi dependence, the general solution of Laplace's equation, which we then have to fit to boundary conditions, general solution
Whoa.
General solution is E of r and theta will be the sum from L is equal to 0 to infinity. L can start with 0. LL plus 1 would be 0 in that case, but that's okay, it turns out. That doesn't, because P0 is 1, so it doesn't go away, so it's not a trivial solution. L equals 0 to infinity of A sub L r to the Lth power plus B sub L over r to the L plus 1th power. I don't know if that's really, say that, L plus 1, but I did. PL of cosine theta. So this is what gets the box. Once again, we've written our solution as an infinite series of separable solutions. Here's the r of r term, here's the theta of theta term, and in general, some of the boundary conditions will allow coefficients to fall away for us, and then we're going to have to do a sum in order to fit some boundary condition. Because it turns out that just as the sines and the cosines form what we call a complete orthogonal set, we can express any function in terms of a sum over sines and cosines that fit the boundary conditions, so too we can express any function of theta as a sum over Legendre polynomials. Any function of theta between 0 and pi can be written as a sum, an infinite series of Legendre polynomials, because the Legendre polynomials also are orthogonal to one another. If you integrate PL of cosine theta times PL prime of cosine theta d theta, actually times sine theta d theta, because we're in spherical coordinates, so we're using the area element sine theta d theta kind of thing. Well, and anyway, never mind. Sine theta d theta, get an orthogonality condition. It's some constant if they're equal to one another, and it's equal to 0 if they're not equal to one another. So we'll do the same thing we did with the Fourier series. You fit the boundary condition by multiplying by PL prime of cosine theta, sine theta, and then integrating, and then things fall away, and happiness and joy are ours. And that's what you can be looking forward to all weekend